Good morning, everyone. Let us start this session. So in this lecture, we will solve the problem on the equilibrium of the beams having the fixed support. Okay. So in the last lecture, we have seen the problems on the equilibrium of beam having the roller support and the hinge support. So this is one problem having the fixed support. So here we have to find out. So question is determine the reactions at fixed support A. Okay. So we have already seen what is meaning of a fixed support. So suppose we have one beam which is a AB, okay, and it is fixed in the wall like this. So at the point B, when we draw the free body diagram, then we will show three reactions, okay, because fixed support, so this is your fixed support, it will not allow any kind of motion, okay. So it will offer two reactions similar to the hinge support. So for the hinge support, we have vertical reaction. So right now it is a VB. Then we have horizontal reaction, which is the HB. And addition to this VB and HB, there is one moment reaction. Okay. So that moment reaction, it will be like this. So this is the MB. So these are the three reactions at the fixed support. So because of these three reactions, for the fixed support, there will not be any motion. So the object or the beam, it will remain fixed with the wall. So by referring this free body diagram, we will draw the free body diagram for the given beam, which is a AB. So this beam AB, it is loaded as shown in figure. So this is the UDL, that is called as a uniformly distributed load. It is having the intensity 2 kilonewton per meter. Okay, and this UDL, it is distributed over entire span of the beam, that is 3 meters. Then at point B, there is one moment couple. Its magnitude is 15 kilonewton meter. So this is the additional moment given at the point B. So whenever we draw the free body diagram, we have to consider this moment as it is. Okay. So for the free body diagram, just draw the beam AB. So this is your fixed point. So this is the fixed support. Okay, so for free body diagram, we have to draw the beam AB as it is. Then we have to convert this UDL into point load. Okay, so you know the conversion, how to convert the UDL into point load. So the point load, because of this UDL, it will act exactly at the center of its entire span. So this is the point load due to UDL. And this will act at the point which is a L by 2. So this is 3 by 2. So it is 1.5. And this is 1.5. Okay. Now this magnitude of point load due to UDL. So the point load due to UDL, which is a F, it is equal to intensity into the span. So intensity is 2 kilonewton per meter into total span of the UDL is 3 meter. So this is the total span from A to B point. So this is equal to 6 kilonewton. Okay. So this value, this is equal to 6 kilonewton. Now next we have to show the reactions at point A. Okay, so A is the fixed support. So it will have first two reactions. One is vertical reaction VA. Okay. Second is the horizontal reaction. So horizontal reaction, you can assume HA on the positive side, or even you can assume HA on the negative side. So you can show the reaction at this point HA like this. Okay. So just I will consider HA on the positive side only. So these are vertical reaction and the horizontal reaction, and we have to show the moment at the point A. That is called as a moment reaction. So this moment reaction I will show like this. So this is the moment A. Okay, so these are the three reactions at the fixed support. So always remember, for the fixed support we have three reactions: VA, HA and the moment reaction. Now here I have considered this moment to be clockwise. Okay, you can assume initially moment to be clockwise or anti-clockwise. Okay, after using the conditions of equilibrium, that is summation fx0, summation fy0 and summation of moment 0, you will get the correct direction of your moment reaction. Okay, so right now I have assumed moment to be clockwise, and there is one additional moment which is a moment couple given in the problem, and it is at point B. Okay, so we have to show that moment couple as it is, and right now it is given as a clockwise. So you can observe here, this is the direction. Okay, so at this point I will show that reaction like this, and this value is 15 kilonewton meter. Okay, so don't get confused in the unit of moment and the intensity. So intensity is kilonewton per meter and moment is kilonewton meter. Okay, so this is your complete free body diagram for the given beam, which is a fixed supported. So after this, we have to observe total unknown in the given problem. Okay, so here some x distance given. So just forget about this x distance. Okay, so we will not consider that x distance for this problem. Okay, so total unknowns we have: one is a VA, second is the HA, and third is the moment at point A. So we have three unknowns. So to solve this problem, we will use the conditions of equilibrium. So we have three conditions. One is summation fx0, summation fy0, and summation of moment 0. Okay. So by using these three conditions, we can find out the three unknowns. Okay, so here I will use the summation of moment equation. So from this equation, I can find out this unknown value, which is the MA. Okay, so let us see how to use that equation. So by using the condition of equilibrium, which is a summation of moment by all the forces in the system about the point A. So I will select the point A as a moment point, and this is equal to 0. Okay, so this is the condition of equilibrium. So take the moment about the point A by all the forces in the system. So here we have force 6 kilonewton at distance 1.5. So moment will be 6 into distance is 1.5. Now this moment, it will be anti-clockwise. So this force 6 kilonewton, it will try to rotate this beam AB in the anti-clockwise direction about the point A. Okay, so this is positive. So next force is VA. So VA is passing through the point A only. Okay, so there is no perpendicular distance with respect to point A, so that moment will be 0. Okay, so moment by VA, it will be 0. Then moment by HA, it will be 0 because HA is also passing through the same point A, so that moment is 0. And there is one additional moment given, which is a moment couple, and its value is 15 kilonewton meter. So we have to just add or subtract this value. Okay, do not multiply this value by the distance. So right now distance is 3 meter. Okay, but for the moment we don't multiply by the distance, just add or subtract that moment. So right now this moment, if you observe, it is a clockwise. So just subtract this moment. So minus 15 kilonewton meter, and this is plus. So here you can observe there is one moment given, okay, which is actually a moment reaction, which is a MA, and it is right now clockwise. Okay, so clockwise means minus MA, and this is equal to 0. So this is your complete moment equation. Okay, so right now here moment A is not 0. Moment A is acting at the point A only. Okay, but moment we consider directly in the moment equation. If the force, that is a VA and HA, they are passing through the point A, okay, and therefore their moment is 0, because moment equation is force into perpendicular distance. So force magnitude is not 0, but this distance, this is 0, and therefore moment is 0 for these two forces, VA and HA. Okay, and this moment, it is a free vector. So we have to consider this vector as it is in the equation. Just consider sign, whether it is clockwise or anti-clockwise. Okay, so this is your complete moment equation, and from this calculate the value M. So here MA will be so this is equal to minus 6 kilonewton meter. Okay, so right now our answer is negative. So actually we have considered the moment to be clockwise. Okay, so this clockwise moment is already considered by negative sign in your equation. Okay, therefore we should get the positive answer for MA only. Okay, but as the answer is negative, that means our assumed direction is wrong. So we will correct that. MA, this is equal to 6 kilonewton meter, and its actual direction, this is the anti-clockwise. Okay, so if you consider the anti-clockwise here, then you will get the positive answer. So if you want, finally you can correct the free body diagram and you can show the moment to be anti-clockwise. Okay, do not again solve the problem, just you can change the direction. So this is your final value of moment and its correct direction. It is anti-clockwise at the point. Okay, so here by using this equation, we have calculated the value of unknown reaction, which is N. Now use remaining two conditions. So by using remaining two conditions, we can find out the HA and V. So use summation fx, this is equal to 0. Okay, so for summation fx, HA is positive because it is on positive x side. There is no other force in the x direction, so HA is equal to 0. Okay, so directly you will get the value of unknown reaction HA. Second, use summation Fy, this is equal to 0. So for the summation Fy, we have the forces 6 kilonewton in the negative y direction. So it is a minus 6. Then we have Va, positive y direction, plus Va. Okay. So there is no other force. This 15 kilonewton meter, it is not the force. So this is the moment. So this is equal to 0. And finally, you will get the value of Va. This is equal to 6 kilonewton. Okay. And Va is positive. So our assumed direction is correct. Okay. So these are the three reactions. Ha is 0, Va 6, positive y direction, and the moment A, this is equal to 6 kilonewton meter, and this is anti-clockwise. Okay. So these are the reactions at the fixed support point A. So in this problem, the beam AB is fixed with the wall at point A as shown, and it is loaded by the UVL. So find the reactions at the point A. Okay, so this is again a problem on the fixed support. So the beam AB, it is fixed with this wall at this point, that is a point A, and it is loaded by the uniformly varying load. This is a UVL. Okay. So for the uniformly varying load, the maximum intensity, or sometimes it is referred as the height, this is given as a 1200 Newton per meter. Okay. The total span for the UVL is a 3 meter, 1.5 plus 1.5. Okay. And question is find out the reaction at point A. So your first step is we should draw the free body diagram. So for the free body diagram, just draw the beam AB as it is. Okay. Your next step is we have to convert this uniformly varying load into point load. So let us see how to convert that. So suppose we have one beam AB, and here we have the uniformly varying like this. Okay. And here we have the height, this side of the triangle. So it looks like as a triangle. So this height, this is given as a W. Okay. Unit is Newton per meter. This total span is taken as a L. So when we draw the free body diagram, then the point load because of the UVL. So this is the point load, because finally UDL or UVL we convert into point load in the FBD. So this point load, this is F, it is equal to, its formula is area of the triangle. So 1 by 2, height W, and its base L. Okay, just consider this total triangle. So base is L, height is W. So this is the area of the triangle formula. So this is the point load, and this point, its distance with respect to this 90-degree angle of that triangle. So this is equal to L by 3. And from other side, that is from this acute angle, this distance is 2L by 3. Okay. So this is the point of application for this point load. So from this free body diagram, we can draw this free body diagram. Okay. So point load, because of this uniformly varying load, it will act somewhere here. So this is the point load. Okay. Its magnitude F, this is given by the same formula, area of the triangle 1 by 2. Now here this side, this is equal to 1200 Newton per meter, and its total base AB, this is 3 meter. Okay, so this is equal to 1800 Newton. This is the force value or the point load. Now this point, it will be at distance, total is 3 meter, A to B. Okay, so 3 upon 3, which is L by 3. So this is 1 meter. So I will write here L by 3, and this is equal to 2 L by 3. So this is 2 meter. So this is 2 L by 3. Okay. Now next, we have to show the reactions at this point at the fixed support. So at this point, we will have 3 reactions. This is the vertical reaction. This is horizontal reaction, HA. And there is one moment. So this is the moment. That is the MA. Okay. So even you can draw reaction like this. If this is VA, okay, you can consider HA positive, and you can draw moment to be clockwise. Here I have drawn moment is anti-clockwise. Okay. Okay, so here we have converted this UVL into point load. Then we have shown all the reactions at point A. So there is no other force on the beam AB. So your next step is use the conditions of equilibrium. Okay. So here we have 3 unknowns: HA, VA, HA, and moment. So first I will use summation of moment by all the forces about point A equal to 0. Okay. So from this equation, I can find out the moment value at point A, which is a moment reaction. So take the moment about point A. So I will start from VA. So that moment is 0. Next, moment by HA is 0, because both these forces, they are passing through point A. So there is no perpendicular distance. Next, this F, its value is 1800 into. Now perpendicular distance of this point from the point A. So that distance is 1 meter. And this moment, it will be clockwise. So here you can see, this is your beam AB. Here we have the force 1800, and this is point A. So this force will try to rotate this beam in this direction. Okay. So this is the clockwise rotation. And therefore this moment, it is negative. So 1800 into 1. So for the moment direction, we have to visualize the rotation, how the force will rotate the given object, whether it is clockwise or anti-clockwise. So this is minus 1801. So there is no other force on this AB, and there is one moment at the point A, which is a moment reaction. And right now we have considered this to be anti-clockwise. So it is positive. So plus ME. Okay, and this is equal to 0. So from this equation, we will get directly MA, this is equal to 1800. This is Newton meter. So this is one unknown out of 3. Next, use the equation summation fx0. So for summation fx0, we have HA. This is the only force in the x direction, and this is equal to 0. So from summation fx, we get directly HA0. So here MA is 1800 Newton meter. It is a positive answer. That means our assumed direction is correct. So this moment, this is anti-clockwise. And after this, use summation Fy, this is equal to 0. So for summation Fy, we have Va in the positive y direction. Next, 1800 in the negative y direction. So it is minus 1800. It is equal to 0. Okay. So from this, we get the Va as 1800 Newton. Okay. So Va, this answer is positive. That means our assumed direction is correct. Va is acting in the positive y direction only. Okay, so these are the 3 reactions. HA is 0, Va 1800, and Ma is 1800 Newton meter in the anti-clockwise direction. So this is how you can solve the problem on the fixed support having the uniformly varying load. Okay, note on the next problem. So this is again on the fixed support, but it carries only the point loads. Okay, so in the previous 2 problems, we have the beam which carries the UDL or the UVL. Okay. So what is given? Determine the components of the support reactions at the fixed support A on this cantilever beam. So cantilever beam means this is one of the type of the beam. So we have seen different types of the beams. So we have to find out the reactions at the fixed support A. Okay. So first step is we should draw the free body diagram. So draw this beam AB. Consider this point to be B as it is. Okay, so this is the given beam. This is point A and this is a B. After this, show the external forces. Okay, so here we have 6 kilonewton, which is the external point load at this point. Okay, so draw that force as it is. So this is 6 kilonewton. After this, we have 4 kilonewton at this point, and this is the direction of that force. So this is 4 kilonewton. This dotted line, it represents the horizontal direction or the x-axis, and this angle given, which is a 30 degree. Okay. Now here, let us consider this point to be C. So from the C point, distance is 1.5. So this is 1.5. From A to C, distance is 3 meter. And the 6 kilonewton, it is at distance 1.5. Okay. Now at the point A, we have the fixed support. So it will have 3 reactions. So this is the vertical reaction. Then this is a horizontal reaction, the HA, and there is a moment reaction. So I will consider it is in the anti-clockwise direction only. So this is the MA. Okay. So this is your complete free body diagram. Now next is we have to resolve this 6 kilonewton, because this 6 kilonewton, it is not in the positive x or positive y direction. Okay, so it is inclined with the x axis. So you can resolve that force. So consider this point for the resolution. Draw the x component and then draw the y component like this. Okay. Now here x component is adjacent to angle 30 degree. So it is a cos component and its value is 4 cos 30. Y component is opposite. So it is a sine component and its value is 4 sine 30. Okay. So now we have resolved this force, and after this you can use the conditions of equilibrium. Okay, so first use summation of moment condition. So summation of moment by all the forces about the point A. So take the moment at point A only. Okay, and this is equal to 0. Now for the moment equation, we have to take the moment by all point loads. So start from 6 kilonewton. So moment by VA, moment by HA is 0. So moment by VA is 0. Moment by HA is 0. After this, we have 6 kilonewton. So 6 into the perpendicular distance of this force from point A. This is equal to 1.5 meter. So this is 1.5. This moment, it will be clockwise. Okay, so if you observe the rotation because of 6 kilonewton, so beam will rotate in the clockwise direction about the point. So it is negative. After this, we have the force which is a 4 kilonewton. Okay, but we have resolved the 4 kilonewton. So just consider these components 4 cos 30 and 4 sin 30. First consider 4 cos 30. So 4 cos 30. So this is the force value into what is the perpendicular distance for